Hello, everyone. And sorry to keep you from your lunch break for a little bit further. I would like to introduce you to our work that we did at Validity Labs on decentralized messaging beyond Whisper. So my name is Sebastian and I'm co-founder and CTO of Validity Labs. We're a blockchain development company based in Zug in Switzerland. And this is one of the, I would say, most exciting projects that we're working on right now. And with this, I would like to start. Actually, the title of my talk is a love story, right, about our two protagonists, Alice and Bob. Some of you might have heard of them before. Now, Alice and Bob, right, so they have this kind of relationship, and Alice expresses her unconditional love for Bob, and Bob expresses his feelings for her in some digital form. You guys like that? Like, would you operate in that way? Yeah, maybe not. Like, how stupid do you think Alice and Bob are, right? They also don't do that. They have, of course, end-to-end encryption, right? End-to-end encryption of the communication between the two parties, and everything should be fine. Now, unfortunately, there is a third party in this relationship. And this third party is Charlie. And while Charlie does not see what exactly the content is that Alice and Bob are exchanging, Charlie knows that these two are communicating, because Charlie is either working at the ISP of Alice and Bob, or she works at some sort of central service provider. So she just knows the fact that these two are talking and is relatively unhappy about that fact, right? So if you think about building such applications in a digital way, which we actually tried here, like working on a project called Mio. So when we worked on Mio, we realized this is not really good enough. So some of the lessons learned that we have to focus on is that end-to-end encryption is oftentimes insufficient. So we do not just have to protect the sender, the message itself, but also the sender and recipient of a message. And that is what we're aiming at with our messaging protocol Hopper. And what we specifically aim for is to provide this metadata privacy that this kind of example that I gave initially should have told you. So we're protecting who is talking to who, when are they talking, metadata such as how big a message is, right? If I see that all of you are sending Ethereum messages and then there's two people exchanging emoticons, which are 3 characters, I learn a lot. Or what IP addresses they are communicating from. All these sort of metadata we want to protect, right, in order to have a privacy-preserving means of communication between the two parties. And the goal of this metadata encryption is as expressed here by Michael Hayden, the former president of the NSA, who said we kill people based on metadata, which is a bit an extreme example of how bad metadata leakage is. Right? But what we want to do is, again, to protect metadata and thereby preserving privacy for both the sender and the recipient. And that's not just actually a problem for our lovers, Alice and Bob, but as we've seen very recently, also for like much bigger organizations such as the Swiss police. So the Swiss police ran into a funny issue recently, and the issue that the data problem that they ran into looks like this. Yeah? Anybody recognizes this car? Yeah? What brand model is that? Tesla, exactly. Now, one of the issues of this great car called Tesla is that you sign one specific clause in the terms and conditions, and that is that a few people can listen to absolutely everything that is happening inside this Tesla car at all times. Now, while that might have a bit more trivial solution, there's further problems with that. If you look at it a bit more closely, you have this smart car, right? We're all into smart technology and smart things and connected things. They leave a huge data trail behind. And that brings us into this problem of intermediaries, such as network operators, AT&T in the US or Swisscom in Switzerland, right? So network operators that now gain insights into, for example, how the police is operating. And we have to ask ourselves the question, is that really good? Yeah? If you're a for-profit entity, do we really want to leak proprietary information to some sort of weird other for-profit entities that are network operators? Does that make sense? And especially if you're, like, for example, a police, you should definitely not leak this sort of data. So that shows us metadata is not just a problem for private individuals, but for a much larger set of people. And what we see today is about these messaging protocols is that centralized web infrastructure, and I think we don't have to talk very much about that here, is largely, by and large, violating our privacy. On the other hand, we see some decentralized infrastructure that are not really having incentives to run it. So for example, if we think about Tor, right? So I don't know how many of you guys are running Tor nodes at home, Tor exit nodes specifically. The problem is that you just don't have incentive to do so, and you have a non-zero cost and non-zero risk, especially legal risk for running a Tor exit node, that you'll run into trouble. So that's one example of missing incentives. And we talk in the Ethereum ecosystem about the incentive of what is the incentive of running a node, right? It kind of goes in a similar direction. Running a miner has incentive, running a node, which is important core infrastructure, is missing incentives. So here we say that mass adoption and scale of decentralized and privacy-preserving infrastructure needs economic incentives, right? So, and this is one of the core aspects that we bring in with Hopper. So basically, Hopper is a decentralized, so it means anybody can participate. To some people, surprisingly, that is different from Tor, right? So in Tor, you have a central entity that is signing off on who can participate as a node in that Tor network and who cannot. Yeah. So Hopper is decentralized. It is incentivized, so you earn money by participating in that network. We'll look a little bit how that works in practice. It is privacy preserving, so we do not only protect the message, but also its metadata. And it's a messaging protocol, of course, so anybody can build on top of it. So it's not our goal here to build a status 2.0 or WeChat 2.0. It's a protocol that any of these other projects can leverage. And how do we do that? We built on this onion encryption that you also know from Tor, where instead of relaying a message directly from myself to a recipient, I do so via relayers. And that's important to understand because privacy is not something that you can get yourself, right? So privacy is something that needs cooperation from others, like quite generally stating that. And specifically here for the application of messages, we do utilize these relayer nodes, which are relaying a message. But what they actually provide to us is not just the service of relaying a message, but thereby producing privacy. Now, why would these guys do that? Well, they earn money for it. And we will now look a little bit more in detail in how that works. So basically, Hopper comprises two layers. It has a message layer and it has a payment layer. And what has to be said is that the payment layer does not de-anonymize the message layer. Now you could think about a naive implementation, right? So you relay some messages and I pay you in Bitcoin. So the thing with that is that if you see on-chain payments that can be linked to the message layer, that this leaks a lot of privacy that we wanted to, that we set out to protect in the first place. So this is the basic layers which we'll now digest in a bit more detail. So the message layer, as I mentioned already, is based on this onion encryption. On a network layer, we leverage a package format called Sphinx that has some very nice properties that are proving upon what Tor does. And we have a first implementation that's building on top of libp2p, which you might have heard from a bunch of other people around here. And on the payment layer, we have basically some fancy payment channels with some additional features and coordinated payout. We have that implemented in Solidity, and for now we have an implementation that we will show in a minute that is running on Robston. So with that, let's get into the message layer. And we will now look at a different interaction. So now it's not just Alice and Bob, it's also their good friends Charlie and Dave. So Alice is initiating a conversation with Dave. She wants to get a message across to Dave. Let's look at how this works under the hood. So Alice is basically finding a route through this network. So she's connecting from her Hopper node to a bunch of other Hopper nodes that she picks on whatever strategy is valid, right? So you might want to, I don't know, have some parties that are trustworthy or that are in very different and opposing sometimes political regimes. So you can come up with fancy strategies for that. So then, of course, she needs some header, right? So she needs to tell Bob where to send the message next. And one important feature here is that every relayer only sees the next hop, right? So Bob does not know, actually, that the message is eventually ending up with Dave. And Charlie does not know that the message actually originated from Alice. So if we look at the header, just in a very simple example here, we have this chain of next hopper addresses, right? So we have this address of Bob, of Charlie. So basically only Bob should see that the message goes as a next step to Charlie. So when Alice is sending this message to Bob, Bob can basically decrypt or unblind this first part of the header information, but not the next. That's important, yeah? So we don't want Bob to de-anonymize the entire chain of traffic. And then Bob has the message, and now we also want to prevent Bob from just extracting the payment and not doing anything, right? Not passing it on. So Bob actually needs the cooperation of the next downstream node, which happens to be Charlie, in order to unblind this payment, which is actually an update transaction in a payment channel. So Bob involves Charlie, passes on some part of the message, and by passing on part of the message, if I go back here, you see that this encryption, Bob takes the first part of this encryption shell off, right? That's what we call this onion encryption. You have these shell layers in an onion-like fashion of encryption. Bob takes that off, and now this body gets passed on to Charlie. And basically Charlie is passing a key half to Bob, with which Bob can unblind this transaction and now sees, okay, this is an updated transaction of the payment channel. So we see the new value that is stored in this payment channel, some payment channel ID and some signature for it, with which Bob can go on chain and close the payment channel if and when needed. And now, of course, the game continues. Now Charlie has the message, and what we also see is that this first part of the routing information is basically removed. So Bob removes it and pads it with some additional info. Again, in contrast to Tor, we don't want to leak that you are relayer number 2. If you know that you're relayer number 2, then you know that the next person is most likely going to be a recipient of that message. So we do that. Now the message is with Charlie, and we repeat the game, right? So Charlie first needs to find out, well, where do I send this stuff to? So Charlie is basically decrypting the first part of the routing information, and is then seeing, oh, I have to send it to Dave. So what she sees there is the hopper address of Dave, and we'll look up in the DHT how to contact actually Dave. We'll contact Dave, and Dave will again collaborate with Charlie to unblind the updated payment channel information. And Dave then has takes off the last layer of the onion encryption. And what we see is Dave is then finally able to see the plaintext message that has been sent by Alice. Yeah. So this is a short walkthrough of the message layer. And although we have touched upon it in this format description, a brief summary of the payment layer works like this: that Alice is basically encrypting the payment. So in this example, it's 200 gig away. It's a relatively small payment for this one individual transaction. So Bob needs the collaboration of Charlie. So receives the second key half to decrypt the payment. With that, Bob now has the 200 gig away. But because Charlie knows, hey, there's actually a message coming into me, Charlie already has received the next part of this payment, which again is encrypted, and with collaboration of Dave can decrypt it. So actually Bob kind of has to forward this payment of 100 gig away to the next relay node. Yeah, and in this way we have an incentive structure for all relayers, and also have kind of prevented that relayers can cheat and have this take the money and run attack. Yeah, so a relayer cannot just extract the value, not relay anything and run away, because they need the collaboration of the next downstream node in order to get that payment out. Good. So that is a brief overview of this message protocol. And with this, I would like to move on to our first public demo. And you see our GitHub repo down here. Our code is open source available. You can look at it. This is a warning also, right? This is the first time we demo this anywhere in public. I'm quite excited about it, but yeah, please excuse us if the Wi-Fi here is not as favorable to us. So I'll connect to Robert. And Robert is going to walk you through a short example of how Hopper works in practice and how you can relay information.
Okay. Well, first of all, you see here, we need, as we are building a decentralized network, we need some bootstrap node. That one is a bootstrap node. This tells new nodes how to connect to the network, how to find other nodes. We have another node, this one, and this one. And of course, we need someone who sends the messages. And let's have another node, this one. And in order to construct such a path through a network, as it is source selected, well, we need to crawl the network and try to find some other nodes. And well, we are lucky, we have found enough other nodes. And now we're able to select one of these nodes, for example, the first one. Let's say, take the first one and send a message to the first node. The first node is identified by this address. I hope you can see it. No, it's not so good readable. And now we can type in a message. And let's send this message to the first intermediate node, that is this one. And we see that this node is now opening a payment channel. The payment channel has this channel ID. And we see here, that node here is receiving the first message. It receives the payment channel opening request. And then we can also see here on Robston that there was most likely some transaction. Well, Robston is a bit slow, but yeah, you see here we have on-chain transactions, so it is live also on Robston. And at the end of the day, you will see that this node received the message. So this was the demo.
Cool. Thank you, Robert. So that was just a first and very early demonstration of what you can do with Hopper. So currently our first testnet comprising 4 nodes is relatively small, but bear with us, we hope it's growing. Yeah, so that gives you some idea of what Hopper can do. And of course, that's not all, right? So there's a lot of stability improvements we need to do that is currently ongoing, especially with regards to opening payment channels. So if we open these payment channels, we need some sort of smart strategy. And currently, as you can guess, the strategy is not as smart. So we open then on demand, right? So that's one. Testing and documentation is, of course, pretty important. And to make it ultimately usable, we need APIs and libraries. That's the next step that we're working towards, right? So the command line application that Robert showed you running on top of Hopper is like one first example, but having a proper library and API for that would be more useful. And finally, yes, we're also looking for funding for that. So if somebody's interested in working with us, do let us know. Yeah, and with this, I would like to close here, and I'm very open to questions. And maybe this is also the right time to give a shout out to kind of a more informal discussion group that we're having here with the Web3 Foundation, with Status, and with some other researchers around here to try to find out how we can really make a useful messaging protocol that is useful for a variety of blockchain and beyond applications, right? That want to be privacy preserving, censorship resistant, and decentralized in nature. That's what we're really after here. And please come to us. Let's discuss afterwards. Let's try to find out how we can make this useful to you guys and how we can structure this from the beginning in a way that's useful to as many people as possible. With that, thank you very much, and I'm open for questions.
So I have a question. So the onion routing is a very good thing, and I have two questions. So first question is it possible to make it dynamic? And the second question, how are you going to have a thought about incentivizing that the second node that is relaying is going to send the data about the transaction verification for this first node? How is it going to happen?
So the first question is around the dynamics, right? So yeah, so that's actually a very good question, because especially if we look at applications like status that are focused on mobile applications, we have nodes, we have a relatively high churn rate, nodes coming in and dropping out. So maybe that's not an ideal, relayer node, because you have a lot of package loss. So you could have multiple paths going out in parallel, but eventually I think that we will have some sort of some sort of reputation system that you see, okay, how online are these nodes? Are they actually available before you send that message? So I would, when I think about what the end game of this is, I don't think the end game is that you have a full node running on every mobile. I think that you have this running in your living room, in your TV set-top box. This thing is running on there all the time, and this thing is online, because that's how you can also generate profits. And the other part of the question was?
The second question, what is the incentive for second relayer give data to the first relayer?
Yeah, very good one, right? So how does actually the next downstream node, why would the next downstream node actually collaborate with the previous node to work here? Well, the next downstream node wants to make money as well, right? So the next downstream node wants to make money, and they can only do that if they gave something back to the first party, right? So thereby we incentivize them to really collaborate in giving something back there. Yeah.
Thanks for the presentation. I have a question about Swarm. So Swarm, a few months ago, they were releasing this messaging system as well. How does it compare here?
Yeah, so basically, what we're aiming for with Hopper is to have point-to-point communication. That's maybe one important one. If you look at several other ones, they're not geared so much towards point-to-point communication, but more for broadcasting. That's one. And then having this incentive layer to operate any sort of this network is another one. Because if you look actually at, Whisper ships with Geth for a while, and it's by default off, right? And I think if it's by default on, we will see quite some people complain, because it does have quite some traffic requirements. We've seen how mobile phones went hot when you used Whisper in that setting. Maybe if you run it on some top-notch machine, you don't bother so much. If you run it on a Raspberry Pi, maybe you do run into issues. So we think this needs incentives. That's one core differentiating factor between Hopper and other approaches that we've seen.
We're good with time.
Okay.
Thank you.
Thank you very much.